Okay, now I can start. I just wanted to address, Clemence, your question that you posed to Guy. I also think that we can consider other different access models to the distribution, which would be interesting. Maybe like the white box circuit model could also have more information that would help us, or other ways. So that's also an approach that I think would be interesting to explore, and we haven't done so yet. So it's another way of looking at it. Okay, so I'll get started now. I'm going to talk in this talk about a very particular thing. I'm going to talk about something that's called the tagged sample and how we can obtain it. Guy mentioned it at the end of his talk. I'm just going to repeat some definitions. So what is a tagged sample? A tagged sample is simply just a sample alongside with the probability of the elements that were sampled. And in this talk, I'm always going to talk about sample D over some domain N. So if we have a collection of samples with their probability, then I argue that it's a pretty useful thing to have. So it can have many applications. One application that we explored is we can use it to decide label invariant distribution properties. Now, as Guy mentioned, these are the properties that remain the same when we permute the domain. For example, again, having entropy k remains the same if we permute the domain. Now, how can a tagged sample help us decide this type of property? So these properties can be decided just from the probability histogram, or the fingerprint, if you're fancy, of a distribution, which means that it's enough for us to know how many elements have probability p for every p. And this is something that a tagged sample helps us to achieve, right? Because if we now draw a sample alongside with a claim about the probability of each element, and we see that half the samples have probability 2 over n, we can conclude that generally half of these mass is on elements with probability 2 over n, from which we can conclude that the support has roughly n over 4 elements with probability 2 over n. And so from the tagged sample, we can conclude something about the probability histogram of the distribution. Now, doing this with sufficiently many samples allows us to decide to know everything about the distribution, save for the labels of the distribution, and so decide these type of properties. But it also has other implications that are not label invariant. For example, if I also get query access to some distribution Q, an explicit description of it, I can also estimate the distance of D from Q using only a tagged sample. I'm not going to go into the details how, but this is clearly not a label invariant property that we can also decide using a tagged sample. And also a tagged sample is also a component in the protocol that Guy just mentioned. So I hope I've convinced you that this is an interesting object to explore. Unfortunately, if we don't have access to a prover, if we just do it by ourselves with sample access to a distribution, it will be hard to compute this object, right? It will require us almost linearly many samples in the domain size, as we've previously mentioned. So in this talk, I'm going to show you how we can verifiably obtain a tagged sample of roughly a square root of n size using square root of n samples and runtime from the verifier. And this would be like the building stone that we use in other protocols. So first of all, let's recall the model that the guy just presented, for those of you who it was still too early in the morning for them to take into account what he said. So again, in our model, we have a verifier and the prover. There's a distribution D over domain N. We want the verifier to draw a few samples. And at the end of the interaction, we want the verifier to either reject or accept, where in this case, what we hope to achieve is that if the prover is honest, we want the verifier to accept and to output a tagged sample of some size, doesn't matter right now. And we'd also want that no matter how an even unbound and cheating prover tries to lie, no matter what it does, then either the verifier will reject, or it will output a collection of tuples of x and some claim about the probability of x, where that claim is almost correct. I mean, it's almost correct, meaning that pi of x is almost d of x for almost all samples. Now, I'm being intentionally vague here about the soundness condition, and towards the end of this talk, I'm going to be a bit more explicit about what this means. But for the sake of now, this protocol allows the verifier to obtain a good approximation of the tagged sample. Yes.
So dx in the tag samples, dx, are we assuming like a finite precision, or are they approximate to start with?
Yeah, we assume a finite precision. Yeah, we don't. Yeah, even let's just assume that there's some finite precision. We don't want to go.
Because there's an approximation here as well, and I don't know.
True. Yes.
So can you just go back to the
Sure. Here.
does that work also if I have two different distributions?
Two different what? Sorry, I can hear you.
That from two different distributions, for example. I'm just
From two different distributions at the same time. We have thought about that question. There are ways of doing it. Yeah, when you can ask for the probability according to two distributions at the same time, but I think we should take it offline because it's a bit it's a particular question, but it's a good question. Yeah, we've thought about that setting as well. Any more questions before I carry on? Okay, great. So the rest of this talk is devoted to actually showing you how this protocol works, how we achieve this this marvelous object. So let's set now S to be some parameter of size roughly square root of n. And for 2s times, the verifier will do the following. It will flip a fairy coin B. And then if B lands on 0, it will draw a sample from the distribution D. And if B lands on 1, it will draw a uniform distribution from the domain, right? So what V has right now is basically two samples, one from D and one is uniform, both of size roughly square root of n, and they're just somehow intertwined, right? V sends this sample to the prover, which is asked to respond with a probability of each element. Now, it's crucial here that the prover doesn't know where the samples came from. V has his own little secret here, where the verifier knows which samples are from D and from U, but the prover does not. I would also mention here that, again, as Guy mentioned, all the prover has to do is to know the probability of each element according to D. And this is why we think that if the prover is honest, it doesn't need to be very, very complicated. It can run also in quasi-linear time. Okay, so if we are in a perfect world and we had known that P is honest, then this would be done right now, right? Because V at the if P is honest has a correct tagged sample. V just can look at the elements sampled according to D, and now there's a claim about their probability, and if it's correct, it's all good. So what we need to do now is to verify the prover's answers. How do we know that the prover didn't lie? So in order to explain how this works, let's focus on some subset of samples, just some samples. Assume there's like T samples that the prover claimed have probability 2/n. I'm not going to explain how the verifier checks that this claim is correct over these specific samples. We can afterwards repeat it for other probabilities, and I'll elaborate more on how we expand it later. But let's just now focus on this type of claim. So the verifier, in order to verify this claim, performs two tests. The first test is consistency test. What I mean by that? Now, every element with probability 2/n should be twice as likely to be sampled according to the distribution D than to be sampled uniformly from the domain. Therefore, since we have roughly the same amount of elements sampled according to D and according to U, to the uniform distribution, the verifier checks to see whether the number of elements tagged 2/n under the distribution D is twice as large as the number of elements tagged under the distribution U. This is the first test it performs. The second test is that the verifier just tests that the average probability of elements tagged 2/n is correct. How is this performed? It just draws a fresh sample D and counts the empirical mass of the elements already tagged 2/n. Now, since you recall that we picked S to be square root of n, this should be well concentrated and fine, assuming that T is large enough. So let's assume that T is significant. And this is also the reason that we have a square root of n in the sample. Just we want this test to be well concentrated. Great. It'll not probably very hard to convince you that these tests are complete, right? If the probabilities of the elements are truly 2/n, then from the hand-wavy explanations I just provided, you can see that it's both consistent and the correct average. The average probability is indeed correct in these two of n. And in this point, it will be probably good to say that I'm sweeping some things under the rug here. First of all, I'm not taking into account concentration of measure, which I will address at the end of this talk. And obviously, we'd also expect the number of samples not to be equal to the number of elements. There might be elements that appear a few times in the sample. But again, I'm not taking this into account as we don't consider as they're a slim fraction of the total number of samples, especially in this regime. Great. So before I start analyzing the soundness of this protocol, this is the entire protocol, by the way. There's nothing more to it. So any questions about the tests, about the protocol? Great. So I'll carry on. So why is this sound? So let's see, let's consider what the verifier has done, right? The verifier sampled bits and the elements from the domain. And it did so according to procedure number 1, right? First sample the bit, then sample X. But for the sake of the analysis, let's just amuse ourselves with procedure number 2. Imagine that the verifier could have done this as well. It could have drawn X according to this convex combination of D in the uniform distribution. And then based on X, the verifier could have decided the bit B, right? If for a certain X, it will set B to be 0 with probability proportional to the mass of X, D of X over D of X plus 1 over N. And it will set B to be 1 with probability 1 over N over D of X plus 1 over N. Now, obviously, the verifier cannot sample according to procedure 2. Right, because in order to sample this, you have to know the probability of X. It cannot be done. So the verifier can only sample according to procedure 1. But luckily for us, these are the same. The distribution produced by procedure 1 and procedure 2 are the same distribution. And even more luckily for us, from P's perspective, V might as well have sampled according to procedure number 2, right? Because all the prover sees is a bunch of elements, and it doesn't know the bits, And so we're going to analyze the soundness of this protocol, taking into account that this is the way that the samples were drawn, namely the second procedure. Any questions about this? Yes.
Just to understand, so what you're saying is, in some sense, the secret
that the verifier has is that the prover doesn't know whether X was generated from D or from the uniform, and that's what it's going to exploit.
Exactly. Precisely, thank you. So this is the meaning of keeping the bits secret. So let's see how this helps us, okay? So we now think that the prover gets the samples, then decides which samples they want to tag 2 over n. And now let's try to think what conditions do the samples that the prover wants to tag 2 over n must comply with. So the first condition is the following. If we take a random sample tagged 2 over n, what needs to happen is that the average probability that it was sampled according to D has to be twice as large that it was sampled according to the uniform distribution, right? And again, let's assume full support of D. I don't want to take into account what happens with the denominator is 0. So this is kind of rewriting test 1. Because the B's are set after the fact. And test 2 doesn't have to do with all this fancy stuff. We just want the average probability of dx if we sample a random, a uniform sample tag 2 over n. We'd want the probability d of x to be 2 over n. Okay, this is just rephrasing the protocols under the assumption that the samples were drawn this way. Is this clear? Questions about this? Because this is the important bit. Great. So again, if I just plug in what it means to sample the bits after the fact, I can replace the denominator and the denominator with these expressions, which brings us to here. And again, by simple manipulation, just multiplying by n, we get this condition right now. And this is very nice, because what we get here is actually that the set of samples that the prover chooses to tag 2 over n has to satisfy these two conditions. namely that if we draw a uniform sample from this set of samples, then the inverse of its probability has to be 2 over n, and the average probability has to be n over 2 and 2 over n. Sorry, that's what I was meaning to say. And Jensen's inequality tells us that this could only happen if d of x is a constant random variable. Or in other words, if these two tests pass, we know that for every x, the probability of x is the same as the expected value, which is 2 of n, which translates in the language of the protocol to the fact that if the equation is old, only if the true probability, d of x, equals the alleged probability, 2 over n. Great. Was this too quick? Questions? Okay, but of course I was lying. I was lying in two main ways. The first one is we kind of cannot expect the probabilities to be so neatly distributed that you have a lot of probabilities with value 2 over n. What we do is we kind of consider some bucketing. So we bucket together all the elements of probability 2 over n and 2 over n with plus 1 plus epsilon. Yeah, Talia's not here. I was also looking for her with my eyes. Don't tell her. So this is the one way we're lying. So this immediately makes these equations not hold in exactitude, but in some approximation. And the second thing I was lying about is that we don't expect them to hold accurately just because that the equation, the equal sign in the test is not exact. There is some issue of concentration here, right? It would not be exactly, the number of D samples would not be exactly 2 times the number of U samples, and the mass would not be exactly that. There is some issue of concentration here. So this begs the question, is what I just said now robust to these small changes? And it is actually robust in some sense. So what I want to argue is if the alleged probabilities that the prover provides are far from being correct, then these equations don't even hold in approximation. So they're far from being correct, and the tests are, let's say, flagrantly false. I mean, these equations. So let's be a bit, the last thing I want to do now is, and I think we're going to be fine on time. The last thing I want to do now, 5 minutes, great, is kind of explain what do I mean by being far from correct. What is the soundness condition I alluded to in the beginning of my talk? And for some sample x now, that has some alleged probability pi of x, we will define the error over x to be this expression here. Okay, which you can think of some way like some multiplicative quantification of the of how much pi of x is far from d of x. So you can see that if pi of x equals d of x, then the error is 0, and we're all good and happy. But if it's twice as large or half as large, then the error would be half. Now, to motivate this type of error, consider the following setting. Imagine now that pi of x is representative of some distribution over the entire domain, right? Pi of x just assigns probabilities to the entire domain, not just the sample. So if we have this type of probability distribution, and we know that it's far from distribution D by epsilon, it means that the average error would also be quite large. In other words, this is what we kind of try to achieve, right? We want that if the prover tries to convince us that the distribution D is actually if the prover tries to convince us that the values of probabilities of distribution D are actually far from their true value, in the sense that it tries to make us think that D is another distribution that's far from D, then the average error would be high. So what we actually assume in the protocol, that if the average error is high, if the prover is trying to convince us that D is actually some distribution that's far from D, then we reject with high probability. Or in other words, if we assume this soundness condition, at least one of the tests that I presented previously is far from being satisfied. And in that sense, those tests were robust. I hope I managed to convince you that this is a satisfiable definition. Any questions about this definition of soundness or about this quantity? Great. So all I'm left to do is summarize. Hopefully, we're convinced that we can verifiably obtain a tagged sample using only squared event samples in runtime, significantly better than what we could achieve without a prover. This could be very useful for deciding natural distribution properties, such as labeling invariant ones, but also other things. When you just have a bunch of samples and probabilities, you can do many other things, as also exemplified by Guy's talk before. And we still have open questions. For example, lower bound, can we do it? Can we have smaller tagged samples with less communication, or it's an open question. Can we have other applications for them? And can you have like, can we have them tailor-made for specific properties and general ones? And that's it. I'm also looking for a postdoc position, but I'm also going to talk about this in the graduating bits part. But yeah, that's it.
So there is the coffee break there, but we have time for questions. So if there's any questions.
So this is a bit speculative, but so what your verifier is doing is effectively checking sums of probabilities, right? It's basically like it gets some elements, and for some set of elements, it's trying to check that the total mass is correct.
In the second test. Yes.
That's the basic consistency test seems to be that. Do you think one can come up with consistency tests that do something more? Like for a set, I can try to measure the collision probabilities, like the sum of squares or some sum of higher powers, and whether that would lead to alternate protocols. Maybe you can shave off log n factors or something with that. I don't know. Does that?
In some sense, we do consider a higher. It's hard for me to answer this because I conceptualize the tests a bit differently.
Okay, I can say, isn't it a plus that you can verify like only? All you need to do is verify this, so your sample complexity is small. If you needed to verify higher moments, you would need more samples.
It's not obvious. Like sum of squares sometimes is a collision probability, and that's actually
so. In fact, the second test here is collision probability, because if you can, I'm phrasing it in this sense of average mass, but the expectation here is over the distribution, so it's effectively the second moment. So you can think of the first one being the first moment, but then the second one being the second moment. The public coin result that Guy referred to earlier has the third moment as well. Like instead of using, and it uses more samples, instead of using the first test, it's replaced by another test for the third moment, but it's much more taxing in terms of samples. So there are ways of using higher moments. It's just, this was the most efficient in terms of sample complexity for the verifier.
Does the public coin use for the same problem?
Yes, the public coin protocol obtains also a verified tag sample, with the difference that the sample complexity is n over 2/3 instead of, because it also approximates. You can think of the second test here as an approximation of the second moment, and the third and the public coin protocol does without the first test, which is the secret coin part, and adds another one, which is the third moment, which again, it's kind of checks uniformity. Yeah.
Yeah, so I had a question about this. So once you framed it that way, getting tagged samples, so there's a paper with Ronit, and then there was a follow-up with Christoph and Son that was on probability revealing samples, which is exactly that. You assume you have that magical black box that instead of giving you IID samples, gives that a sample with its probability. And then a lot of things could be done much more efficiently. So I was wondering if you had looked at those properties and see like what you can get.
I actually have not.
Okay.
But I think it's a great thing that I should do.
I think one issue is to what extent these results are robust to errors.
Right.
Yeah, multiplicative noise, multiplicative is okay in the priorities. Yeah. Okay, so let's thank Tal again and maybe continue over the coffee break. I think I have more questions. And oh yeah, and there is